What if a dead star was hiding a secret identity? What if something that looked completely normal for 20 years turned out to be the aftermath of a cosmic collision so violent it nearly triggered a supernova? Well, Hubble just caught one. And by the end of this video, you'll understand why this single discovery could mean there are thousands of disguised stellar imposters lurking in our galaxy, and why that matters way more than you think. Here's what we're going to cover. First, what white dwarfs actually are and why they're the universe's most overlooked objects. Then, the specific clue Hubble found that blew this case wide open. We'll talk to Dr. Snehalata Sahu, the astrophysicist who led this discovery, about what makes this object so unusual. By the end, you'll see evidence that challenges our understanding of stellar death, stellar mergers, and what the graveyard of the Milky Way is actually made of. By the way, we uploaded our full uncut conversation with Dr. Sahu exclusively for our Type 3 Civilization members. Link is in the description. All right, so before we get to the discovery itself, you need to understand what white dwarfs are and why this one broke the mold.
White dwarfs, as we know, so these are dense stellar remnants that are left behind when a star like our sun dies. So this white dwarf is similar to that. But the unusual thing about it is that it is very extremely massive, 20% massive than the sun, and it does not appear to have formed from single stars. So usually other white dwarfs, they are half as massive as sun and they are thought to form from these single stars. Like generally when the sun runs out of fuel, it evolves and to a white dwarf. But this particular white dwarf, our evidence suggests that it does not form from the single star, but rather it would have formed from the merger of two stars.
So let's put that in perspective. Most white dwarfs are about half the mass of the sun. This one is 1.2 times the mass of the sun, packed into something roughly the size of Earth, about 8,000 miles across. That's like taking an object 865,000 miles wide and compressing it into something you could almost drive across in a day. And as she just said, this thing is too massive, too unusual to have come from a single star quietly running out of fuel. Their evidence points to something way more violent. Two stars smashing into each other. But here's the problem. Once a white dwarf forms, the evidence of how it was born gets buried under thick layers of hydrogen and helium. So this white dwarf, WD0525 plus 526, sits just 128 light years from Earth. In cosmic terms, that's practically in our backyard. It's like living in New York City and finding out your neighbor 3 blocks away has been leading a double life. For almost 20 years, astronomers looked at this star in regular visible light and saw absolutely nothing unusual. Standard hydrogen atmosphere, completely normal white dwarf. So what changed? The team pointed Hubble's cosmic origin spectrograph at it in ultraviolet light, and what they found shouldn't have been there. Traces of carbon. Now, to understand why this is such a big deal, you need to know that 6 other merger remnants had been found before this one. But those all had huge, obvious amounts of carbon you could spot in regular optical light. But this star, totally different story.
The other previous white dwarfs, which have similar merger history, they have large amounts of carbon. That's why we were able to detect in optical. However, for this carbon, the tiny amount, it's 100,000 times smaller than what we detect in other white dwarfs, the amount of carbon. And this carbon is important because generally white dwarfs, they are composed of different elements with heavy elements like carbon, oxygen sitting in the interior, while the lighter elements, helium and hydrogen in the top. So detecting these tiny amount of carbon reveals that carbon, which has formed deep inside the star, it has come out to the surface, revealing that something would have happened in the past. So it gives clue about the star's interior structure and the past history. Since we cannot core deep in the white dwarf, so getting this tiny amount of carbon in the atmosphere, it gives important clue that it has formed from the merger of two stars.
Let me make sure you caught the key part of what she just said. The carbon is 100,000 times less than what was found in other merger remnants, and that impossibly faint signal is what rewrote this star's entire history. Because we can't drill into a white dwarf, we can't take a core sample. So, when carbon from deep inside manages to float up to the surface, even the tiniest trace is like getting a message from the star's past. And the reason this star fooled everyone for so long? The mistake most astronomers were making was a totally understandable one. They looked at this star in optical light, saw nothing unusual, and assumed it evolved from a single star. Even now, if you pointed a regular telescope at it, it would still look completely normal. Turns out the evidence was there the whole time. It was just invisible in the wrong kind of light. This is where the concept I'm calling the imposter effect comes in. If this star looked perfectly normal for 20 years, how many other white dwarfs might also be disguised merger remnants? But that's not even the craziest part. Stay with me, because the way this carbon actually reaches the surface involves a process that was basically theoretical until now. In the 6 previously known merger remnants, the answer was regular convection. Hot material rises, cool material sinks. Everything gets mixed. But WD0525 plus 526 is way too hot for that. At nearly 38,000 degrees Fahrenheit, the outer layers are stable, no churning. The answer involves something called semiconvection.
Before understanding semi-convection, let's understand convection. So you can take everyday example of boiling water in a pot. So when we boil water, the hot water rises, which is beneath the bottom, and the cool water sinks. So this process leads to the mixing of the material. The liquid gradually mixes. So this is called convection, which we generally observe in stars and white dwarfs. However, there can be some scenario where there can be different layers of composition. So boiling water is one composition, but let's just add salty water and fresh water above. So that difference in the composition, it can slow down the mixing. So that's what we call semi-convection. So in this particular star, there is a difference of composition of carbon and hydrogen. So these difference, since hydrogen is very less and very thin, and carbon, so these difference in composition leads to slow mixing rather than the vigorous mixing like in boiling water. So we can call this as semi-convection. So this slow mixing leads to tiny amounts of carbon to appear in the surface.
That saltwater analogy is perfect. Regular convection is a full rolling boil. Everything mixes fast. But semi-convection is what happens when you've got layers of different stuff. The difference in composition slows down. Just a gentle simmer. And that gentle simmer is just barely enough to let a tiny whisper of carbon seep up to the surface. This process had been predicted in theory, but this is the first time it's been formally identified in a real white dwarf. Now, if I were you, the thing that would be biggest on my mind right now is, sure, they found carbon and have a clever explanation for how it got there. But how do they know for certain this star is actually a merger product? Couldn't there be other explanations? The team thought about that a lot. They systematically tested every alternative. Could the carbon have come from a planet falling into the star? If so, you'd expect to see silicon, iron, and nitrogen alongside the carbon. They checked the UV spectrum carefully. Only carbon, nothing else. Planetary debris ruled out. Could it be interstellar gas drifting in from space? They checked the velocities against known interstellar medium models. Didn't match, ruled out. They looked for infrared excess from a debris disk. Nothing. They looked for brightness changes from a companion. Nothing. On top of that, the star is 1.2 solar masses with a hydrogen layer billions of times thinner than expected. Their models for normal single-star evolution simply cannot reproduce what they observed. Every single alternative fell apart. The merger was the only explanation left standing. And that brings us to the part that should genuinely keep you up at night. But remember the previous 6 white dwarfs? All 6 were spotted in optical light because they had huge, obvious carbon signatures. 6 out of billions of white dwarfs in the Milky Way. But WD0525 plus 526 is the first merger remnant identified solely through ultraviolet spectroscopy. Its carbon signal was 100,000 times fainter than those other 6, completely invisible in visible light. So the worst possible conclusion astronomers could draw, that those original 6 were the full picture. We asked Dr. Sahu what this means for the bigger search.
We need UV observations, otherwise it's like other white dwarfs, many more might be hiding, and we don't know the fraction of such merger remnants. So only UV observations of very large population of white dwarfs, if we study them, then only we can know that what is the fraction and we can improve our models. So the definitely UV observations is needed, and any future UV instrument will be very good for this.
Let that sink in. Without UV observations, these merger remnants look identical to ordinary white dwarfs. They blend right in. We don't even know what fraction of white dwarfs are secretly merger remnants. The answer could completely reshape our understanding. These merger remnants are directly connected to one of the biggest questions in astrophysics. What causes type 1a supernovae? Those are the thermonuclear explosions astronomers use as cosmic measuring sticks to map the expansion of the entire universe. If we're wrong about how many merger remnants exist, we could be wrong about how often these supernovae happen. And that ripples out into everything we think we know about dark energy and the ultimate fate of the cosmos. So, let's bring it all together. For 20 years, this star looked completely normal. Then Hubble looked in ultraviolet and found a trace of carbon 100,000 times fainter than anything detected before in a merger remnant. That tiny signal revealed that a star everyone assumed was ordinary is actually the aftermath of a violent cosmic collision. Semiconvection, a process that was basically theoretical, explains how that carbon whispers its way to the surface. Dr. Sahu and her team tested every alternative, and the merger was the only explanation that survived. And the real kicker? We don't even know how many more of these stellar imposters are out there, hiding behind a mask of hydrogen, waiting for someone to ask the right question in the right light. Now, here's my question for you. If one UV observation rewrote the history of this star, what else do you think is hiding in plain sight across the Milky Way? Drop your best guess in the comments. And if you want to see what happens when white dwarfs push physics to the absolute limit, you're going to want to watch this video next about what might be the fastest spinning white dwarf ever found.